Hi there, and thanks for tuning in. Today's notes are going to be lesson 3.7, part 1, graphing absolute value equations. We're going to be looking at 5 things to write down in our notes today, so let's go ahead and get started. This first page has a lot of information on it, so I'm just going to basically highlight or underline the things that I need you to make sure that you understand. An absolute value function is a function that contains an absolute value expression. The parent absolute value function is f of x is equal to absolute value of x. The graph of f of x is V-shaped and symmetric about the y-axis. The vertex is the point where the graph changes direction. So that's another important thing, sorry. And then the vertex of this graph is at 0, 0. Okay? And then maybe you would draw what this graph looks like, because you're going to be comparing different absolute value graphs to this one right here. So the things that are underlined and highlighted around, let's go ahead and take time now to pause the video here. You should know about the domain and the range. The domain is going to be all real numbers because it's stretching through all the x's, and the range just has to be greater than or equal to 0. Okay, so let's go ahead and pause and write, and then once you're done, click play. The next thing we're going to do is actually graph an absolute value equation. It says graph each function and compare each graph to the graph of the parent function. F of x is equal to the absolute value of x. Describe the domain and the range. So all you need to do, and it's very simple, you're going to make a table of values using positives and negatives, plot the ordered pairs, and then draw the V-shaped graph. So what I did first is went ahead and made my x values range from -2 to +2. Sometimes you might need to go larger outside of that just so you can see this symmetric on each side, but in this case I think it will show the symmetry. The next thing we want to go and just plug in these. So if I plug in -2 for the absolute value, that's just going to change it to a +2. So it's really just 2 plus 3, and that gives you 5. I'm going to do that for each one of these values now. So here are all my values. Now I'm going to take the time and plot these points, step 2. So -2, +5, 1, 2, 3, 4, 5, and like the same thing. So here are all my plotted points. I can go ahead and now connect those using a straight line. And then thinking about your parent function. I'm going to do the parent function here in red. Remember, parent function was f of x, so basically 1, 1, 2, 2, 3, 3. So here's the parent function. So it's basically identical to the parent function, except it is translated 3 units up from f of x is equal to x, absolute value. Okay. The domain here for the purple one, the domain would be all real numbers, and then the range would just need to be y is greater than or equal to 3. Okay. So that's what you're going to do for the next few. Make sure you make the table of values, plot the ordered pairs, and then draw the V-shaped graph, and then answer the question, how does it compare to the parent function, and then describe the domain and range. So here's another one, here's another 2 that you're going to try. Again, make sure you use enough values so that you can see the symmetry over the y-axis. So let's go ahead and pause here so you can try both, and then once you're done, click play. Okay, so what I've gone ahead and done for number 2 is fill in my table, and now I'm ready to plot my points. So I have -2, +1, -1, 0, 0, -1, so there's my vertex, 1, 0, and 2, 1. So here's what my line looks like, and according to the parent function, this was translated 1 unit down from f of x is equal to absolute value of x. Okay, the domain and the range, domain would still be all real numbers, and then the range just needs to be y is greater than or equal to -1. Okay, let's go ahead and look at number 3. So I'm going to scoot this up a little bit so we can see what number 3 will look like once filled in. And the reason why I started with -6 as my smallest value or my smallest domain value is because that's going to give me -4 to get to the vertex. This is what it looks like. -6, +2, -5, +1, -4, +0, -3, +1, and -2, +2. So here's your vertex here. And this one has been translated four units to the left from your parent function. So maybe even consider what you're seeing in the absolute value. This one was translated 1 unit down. This one was translated 1 unit to the left. So there should be a kind of a pattern that you're going to start to see here. Okay, your domain again would be all real numbers. And your range for this one, y would just need to be greater than or equal to 0. Okay. Next up, we just have our last two in our notes. So again, we're going to go ahead and try these, making your table, describe and compare the graph to the parent function, and then find the domain and range. So let's go ahead and pause here, and then we're going to see what happens with these absolute value functions. Okay, so what I've gone and done is made tables for each of these. I'm going to go ahead and fill out number 4, where t of x is equal to -3 times the absolute value of x. So we'll have -6 as one of the values, and then -3, 0, -3 again, and -6 again. Okay, so let's look at this to see what happens when we graph it. So here are my points plotted, and when I connect, I notice that it is looking a little bit different than my parent function. There are two things that have happened here. It has been reflected over the x-axis, and it has been, we'll call this stretched by a factor of 3. So sometimes you can stretch it and sometimes you can shrink it. Just kind of depends on what has happened. Normally stretching occurs when you're multiplying by a whole number, and shrinking will occur when you're multiplying by a fraction or a piece of a number or decimal. Okay? And then your domain would be all real numbers, but your range would need to be y is less than or equal to 0. Okay? Over here in number 5, I use the numbers that would be easiest here. Whenever you're multiplying by 1/4, I wanted to get whole numbers, so I used -8, -4, 0, 4, and 8. So I would get 2, 1, 0, 1, and 2. So let's see what this one looks like after we graph it. So here are my new points graphed, and I'm going to try my best here to make a straight line. And you can notice that this one has been definitely messed with a little bit. Since we multiplied by 1/4, we're actually going to call this a shrink, and a shrink. So this would be a 1/4 of a normal parent function. So we would call this a vertical shrink. Of 1/4. I know that's hard because right now it looks like it was a stretch, but since it's been multiplied by a part of a number or a fraction, it's going to be considered a shrink instead of a stretch. Okay, just make sure you keep those two in mind whenever you're talking about stretching and shrinking. That is going to conclude our notes for today. Thanks so much for tuning in and just having patience with all those graphing questions. We'll catch you next time for our next video.